of physics, let's take a flight with magnetism's wonder shining so bright from the north to the south.
Hello everyone, I hope everyone is doing well. Today we are going to introduce the lab for induced electromotive force, which basically from Faraday's law says that when there is some change of magnetic flux that is going through a coil, there's some induced electromotive force that is going to be produced on this coil. So basically, let's start with a coil. If you have a coil like this one, you connect this coil to galvanometer or a voltmeter. So basically, let's imagine that we are connecting this one to a voltmeter here. So basically, if we have a magnet, north and south, basically this magnet has some magnetic field around it, as we all know. Some magnetic field. Let's say this magnetic field is B. So this magnetic field is going to go until it becomes basically inside this coil. But Faraday's law is saying that this magnetic field is creating some phi or flux, which basically the magnetic field going through a cross-section area of this coil. So we have some phi here, some flux or magnetic field inside the coil, but it's constant. If this permanent magnet, it's in this position, does not move, so this flux is constant, which basically is equal to the change of the magnetic flux equal to 0. So the electromotive force induced in this coil basically is equal to 0. Only when this magnetic field starts to change, which means that we either approach this magnet towards the coil itself or go away from it, that means that the magnetic field or the flux crossing this coil is changing with time. Only at this situation we are going to introduce or induce some electromotive force or some voltage across this coil. And we can see from this formula that we have here, the faster the change, the higher the induced electromotive force. Okay? And the more the turns, basically because it depends on n number of turns inside this coil, when you have more turns, basically, that means you are going to have higher electromotive force or induced electromotive force when there's some change in the flux going inside. So here, we still have one thing, which basically this negative sign. So this is from, or let's say this section, it's from Faraday's law. And this one from Lenz law. And this sign means that the induced electromotive force that is produced in this coil, it's produced in a way that opposing the action that's happening here, which means if I am going with this magnet and approaching towards the coil, that means the coil has to produce some magnetic field, or the electromotive force that produced here is going to create some magnetic field that's opposing the increment or the increase of the magnetic field. Okay? And basically if this magnet is going away, that means that this coil is going to produce electromotive force so that the magnetic field produced inside, it's kind of opposing the action of this one to decrease. So it's trying to push it inside. Let's explain the Lenz law. Which basically the induced electromotive force should oppose the action that's happening from the magnetic field. If the flux of magnetic field is decreasing, it opposes this action and try to increase it, and vice versa. So let's see this one. So if we have a coil here, let's imagine that the coil, like kind of this way. We have here voltmeter, for example. So we can see here. So the coil itself, just to see how it rotates here. So basically it was N, then goes inside, outside, inside, outside, inside, outside. Okay? I hope you see how is it moving. From here, it's out, inside, out, inside, out, inside. So here, let's have a magnet, has north and south. Let's assume that the magnet is going inside. So basically it's going inside. It means that the magnetic field is approaching here from the north itself. So it's increasing. So if it's increasing, I need to create some magnetic field on the other side to oppose it. Okay? So we need to create some magnetic field here to oppose this action. So to oppose it, basically we need to have also north here. Okay? So in this case, if the magnetic field, in this case we need to create a magnetic field that is moving in here. So in this case, from the right hand rule, we can make our hand, the curling, in the direction of the magnetic field. So if we came here and we are standing in this direction, so curling like this, so we can see that the magnetic field is in this direction, so the current is going up here. So the induced current inside this coil is going to be in this direction and going like this. So when the current going in this direction using the right hand rule, we can see that the created magnetic field is in this direction. So basically we created here a north, so it's opposing the action or the increasing of the flux itself. Okay? So let's assume the other way. We're going to remove all of this. Let's assume that this magnet is going outside. It's going away. So the flux here is decreasing. That means this coil is going to induce some electromotive force so that it creates a current, a magnetic field that stop this magnet from going away, kind of try to attract it. To attract this one means we need to have here a south. A south means this is a north, and basically the magnetic force around here as well is going to be in this direction. Okay? To have a magnetic field created in this way, basically using the right hand rule, we go in the coil, so it's not going this way, it's basically the magnetic field. We curl our hands, so the direction is down. So we can see that the induced current here, it is in this direction. So I hope you got the idea of the Lenz law. Electromotive force equal to negative of the Lenz law, basically multiplied by N d phi. The idea of the sign itself, the negative sign, and the change of the flux going through the coil itself. So right now we are going to do the experiment using magnets, coils, secondary and primary coils. So let's go.